Okay, Alhiba is recording by now. Okay, she got that. Okay, just let's talk about some of the administrative problems. Many students asking when is the exam. I looked up the website, the university website, and they say that our final should be on the 15th, which is Tuesday, 2 weeks from today. I hope I'm correct. Anybody listening to me can make sure that I'm right. It says Tuesday, 15, 3:30 to 5:30. That's what the university website says. So that's going to be the exam. Does this answer the question that a few students asked about that?
Yes, thank you.
You're very welcome.
Hey, Professor, I had a couple questions. I noticed like you sent out the exams this week, like you sent it out like today. When can we schedule a time with you to like go over it? Because like I noticed a few issues with my exams with the grading. Like how can like I schedule an appointment with you to go over my exam? Or
we talked about it several times. Okay, but let me repeat everything. Okay, let me repeat everything. I hope everybody got the exams back from exam 1. I really hope so. The grader said that he sent everything back. On the second exam, we plan to finish sending you back the exams by the end of this week, or maybe let's say Monday. Okay. So now, what I mentioned earlier is that you guys can look up, and if there's something you feel that was not graded properly, there was an error or whatever, but not just, hey, why don't you give me 5 more points? That doesn't work like that. So you can take the exam that you got back with the grading, email that back to me, and I only have a few students who did that, maybe about 10 of them. So, and I send back responses. When I think it's okay, it's okay. When I'm not, I just, I regrade it. If it's fair, then I give more points. If it's not, then I just leave it as is. So anyway, that answered the question. My email is, jkatz@sdsu.edu, and it's on the website and the department and everywhere and all that. Also, on the final, and again, I'm saying it's going to be on the 15th, 2 weeks. It's not 2 weeks from today. Let me just. It's a little bit less than 2 weeks. Okay. So on the 15th, today we are the 3rd. Okay. So it's 12 days from today. So that's where the exam. I'm going to have the last class on the 10th, and I'm going to go over the material and try to see what we've studied, and maybe you can have a better view of what we did, what we accomplished. And then exam is going to be accumulative, but it's going to be more focused on chapter 7 and 8, which is the high Reynolds standard flow, which was not really covered too much during the previous exams. That's basically it. Any more questions regarding issues like that?
Will this be a longer exam for the final?
Some kind of a flow, and then you want to create lift or negative force. So if you take your hand out of the car and you put it in a certain angle, then the hand is going to be lifted. I guess everybody agrees to that. Don't try that at home because that could be dangerous, but I hope you believe the phenomena. So with that said, we're trying to understand as an engineer, can we predict the magnitude of that force? And we're going to call that lift. And this is what we started last time. This time I would like to conclude it. And of course, like always, we do a kind of generic example. Once we understand the mechanics of it, we do a whole wide range of cases based on some formulation. And usually we have experimental, or in this case, we can have numerical results. But you don't do the numerics, I will show it to you. Okay, can I continue with the class? Okay, so no remarks. Let's start. All right, here is this. So what are we going to do today? As I mentioned, remember, we are in the high Reynolds number flow, where most of the flow is in viscid, and viscosity is or the friction, as we say, is really limited to near the surface of an object. So if you have a car, if you have a kite, or you're flying something, then we're talking about cases like that, and we would like to calculate the forces generated by this object. So if you want to design your kite, how large should it be and what kind of weight can it lift? Things like that. Can you answer the question? The answer, after what we'll do here, you should be able to do so. Okay, so we discussed the concept. I already started that. Okay, just let me repeat what we did last time quickly, and then try to extend and do more examples. So we're going to continue with the option of doing things that we can solve in class. So that limits us a little bit, but we could solve the flow over a cylinder. So now it is very clear that because of the symmetry on the flow over the cylinder, we did not get forces neither to the x direction nor to the z direction. So we need to create some asymmetry, which is like in this picture. Okay, so clearly, if the flow is slower here on the lower side, then we're going to have plus. Here it is faster, then we're going to have minus. So eventually, we're going to have lift. So this is very logical. How can we do that? We took the flow over a cylinder. We just added a vortex. And we did the integration. Of course, the drag ended up 0. But the lift came out rho u gamma, and gamma is that amount of circulation that we added. I also mentioned that this really has to do with solid body rotation. So if this would be some kind of a fluid here, and I had a rod with an area here, and I spin it at a rotation of omega, then gamma would be 2 times the area times omega. So there is a connection, a logical connection between the amount of friction introduced by the boundary, which we call this vorticity, into the flow, and therefore you bend the flow around it. And that is the quantity of gamma. Now, when we did that case, in reality, the flow separates here, separates asymmetrically, still get lift, but the amount of lift is less. So experimentally, here are the results. And this is for a range of higher Reynolds number. We both have the drag and then the lift, and everything depends on the rotation rate, which is what I just said, makes sense. The faster you rotate, you have more negative on the upper, more positive on the lower side. So, and then we have also for sphere, again, the algebra is too complicated for us, but here's the data. So now if you want to calculate something, you can do that, okay? And then we decided to call this one I. So now we're trying to look at the drag and claim that the drag is due to pressure distribution and due to friction. The friction we dealt with before in chapter 7. So therefore, whatever is not the friction, we call it I, but it's a little misleading because in addition to the friction, we're going to have separation, flow separation, and drag due to flow separation. So this I thing is actually called induced drag, and we'll explain it later on today. Okay? So at this point, we understand that we need to have something asymmetric. We did the cylinder, hey, looks good. It doesn't match completely experimental data because they have flow separation, very much like in the case of the drag. But here's the experimental data. So if you would like to make an engineering calculation about a rotating cylinder and estimate the lift or a drag, here you go. So you have enough tool or sufficient tools to do so. All right. So the big issue really, or the more practical issue, is the flat plate. So the case is described here. Okay, we have a coordinate system, X and Z. And then we're trying to find out what is the force as we increase this angle, which we call the angle of attack. We already know that L is equal rho u gamma. That's what we got from the cylinder, but the flow was separated. Now, if we could solve this, actually people solve this by putting little vortices on it. And then the solution comes out that gamma is equal to that thing, which is pi, free-stream velocity, c is the length, and the angle alpha. What is important is here, lift is linear with gamma, and it's linear with alpha. So if I have 2 degrees angle of attack and I have 4 degrees, then I'm going to double the lift. That's a very important conclusion out of that. Not only that, is that this should be, the lift is actually a linear curve. And I'll have a diagram in a few minutes, okay? So you substitute this one up here, and then the end of the day, what I want you to remember is the lift coefficient. What is the lift coefficient? Is the force, the lift, divided by half rho u squared, and then reference area. We're doing 2-dimensional case. This is the 2D case. And therefore, the reference area is going to be the length of the plate, and then unit width. So we call it 1. And of course, it's equal to 2 pi alpha according to that. So if I'm going to look at experimental data, you know what, let me just go back here. If I look at experimental data, this is it. So this is a symmetric airfoil, which is very similar to a flat plate, okay? And I change, here's the angle, I increase the angle, and then the lift goes straight up, straight line, until it separates, until it becomes too large. If the angle is too large, then the flow separates, and then it's not going to work. The lift will drop, and it's called stall. Anyway, so let's keep on where we stopped. So this is what I mentioned, that the CL we calculated. It's coming from exactly the same type of approach within the cylinder, but if you do it on a flat plate, results are good compared to experiment. It's too much for us in this particular course in terms of algebra. Summary, lift is 2 pi alpha, lift coefficient. CD, this would be CDI, of course. I forgot to put the I here. This is the CDI, and it is 0. And I said here, this is, we call it CDI 0. We have to remember that the drag, the real drag, is going to be due to this thing for 2D, which is 0. And then if there's flow separation or there's skin friction. And then one more thing which comes out of that analytical model, which I mentioned, is that the center of pressure is at the quarter chord, because the pressure distribution looks more like this. So more of the pressure difference, more of the lift is up front. Okay, so at the quarter chord, people think that you have a wing and of an airplane and the lift acts at the center. No, it acts closer to the quarter chord. So here is a typical data, and it shows the CD as well. And in this particular one shows that the drag is not changing very much. In this particular case, is the drag, which is mostly skin friction, all the way up to where it really starts to separate here. So it starts to separate a little bit. And the moment, this is the pitching moment about the quarter chord, shows that the center of pressure is exactly at the quarter chord. When it starts stalling, then it kind of goes away. So that's a good approximation. And here's an example of how to calculate. So we said CL is 2 pi alpha. Remember, alpha has to be in radian. So if we said 8 degrees, then it's 8 over 180 times pi. That would be the lift coefficient at 8 degrees or 8 degrees, which is right here. And last time I mentioned that should be very close to experimental data. Okay, so this is just to prove that. Now, I still want you to understand about the shape of pressure distribution and about the center of pressure. What I discussed right now is this one. So again, so I'm trying to tell you stories without proving the math. But in this case, I hope I convince you that the center of pressure is at the quarter core. If I would have a cambered shape like here in the middle, then it's really going to be pretty symmetric fore and aft. And it is true because the flow will be attached, it's going around, it's going to be attached completely. And therefore, the model will compare very well with experimental data. But looking at the pressure distribution, we can see that the center of pressure is at the center. So the point is that if I'm going to have an airfoil or a plate, flat plate, where I'm going to introduce camber, then the center of pressure initially go from here, it will start moving backward because of the camber. Okay, so that's the objective of that particular description. So you'll have a feel of why the center of pressure may not be at the quarter core if you have camber. Okay, here's experimental data to show that. And what people do, so there are two similar, I don't want to call them flat plate, those are airfoil shapes. And experimental data shows that they are very, very similar. Here's again, angle of attack versus the lift coefficient. And once you add a camber, in this case, then at a certain point, you're going to have more lift. Now, if you pitch it to a negative angle, which this case looks more like 3 degrees or something like that, it's probably 3 degrees, then we can call that alpha L0. So this is a -3 degrees. So if I want to find out what is the lift of the camber, therefore, it's going to have the same slope, 2 pi, and then I'm going to have alpha, but it's going to have an additional 3 degree, which is this one. Okay, and don't get scared that I'm going to ask you to calculate that, because that, in order to do so, you have to be able to do the algebra of the more complex case. Anyway, I just want you to understand the effect of camber. So this is how the camber looks like. The important thing is the 2 pi, the lift slope is not changing. Okay, I'll keep on going. Now, I want to be honest with you and tell you the story about the drag. Okay, so this is experimental data, and we can take, so first of all, let's look at this guy, the 2415. It's a 15 means it's 15% tick. And it shows really that the drag behaves like a parabola. Okay, this is the 2-dimensional data. And the reason for that type of parabola is really a little bit of separation starting to get at the trailing edge, and also the flow becomes more and more turbulent. So typically at very low angle of attack, you get the minimum drag, which is the skin friction, which is close to what we calculated with some of the laminar skin friction. But you start pitching it up, you get a little bit more. Now the numbers are very, very small, but still it's going to look like that. Then the more advanced airfoil like this one, okay, this one is actually in the range of up to let's say 0.7, lift 7. It's going to have laminar flow on the top and also on the bottom. So if the flow is laminar, then the drag is not changing because it looks very much like the flow on a flat plate. After that, it stalls, and then not badly, but a little bit, and then you start getting a sharp increase in the drag. So this is just for you to know how in real life the drag behaves. It's not really zero completely, but this component which I'm talking about, this is the CD0, not the CDI, which is a result of skin friction. So the skin friction magnitude, laminar would be this, turbulent, partially turbulent would be this. And then you start adding the flow separation at larger angles, so it's get larger. Anyway, so this is just to explain for you how things are happening. Now, this was a two-dimensional discussion, so let's go to the three-dimensional discussion, which is actually even more important. So I use nomenclature as a wing or airfoil, but you can call that a surface. You can call it a rectangular plate. And our goal is really to understand the lift of a rectangular plate. I will make remarks on some other shapes for those that want to have more information. But if you're on consult exam, or which you are, then we're going to stick only to rectangular shapes. Okay, so that's what it is. So here are definition. B is the span, C is the chord, angle of attack we discussed. The only new term is aspect ratio, which is, I showed you last time, which is B squared over S. That's the definition. In this case, the area is A times B. Therefore, this becomes B over C, okay, which is showing how wide the wing compared to the chord. Here is the camber and maximum thickness. These are some nomenclature on wing and anyway. So I'm saying that the wings will have various shapes. I may give you some information, but we're not going to make things too complicated. I say that we will stick to what I call elliptic load formulas. And for those that don't understand it, don't, but if you would do the algebra, you end up with the ideal case, which is called elliptic loading. So the lift on a plate goes elliptic, maximum in the middle and zero on the corners, because you cannot maintain the pressure distribution at the corners, at the tips. So this is one thing. And another one is, okay, I have the pen. Another one is that the original models came as a vortex model. Why? Because, again, I mentioned that last time, on the lower surface, there is high pressure, negative on the upper surface, so the flow tries to go up here, goes up, and eventually it creates a vortex in the back on the tip, which is called wingtip vortex. So the initial models will be based on what we call a horseshoe model. Why? Because if you introduce an angular momentum into the flow, like we tried to do with the cylinder, and then you cannot stop it. That's Kelvin's law. You cannot stop it, because if you turn something, then the flow turns around. So you really have to keep the same amount of angular momentum. But now this is a representation of the change of direction, but it's the same amount. So the point I'm trying to explain is that the strength of that vortex is the same. Here it is lifting. This is where we created with the angle of attack. And here, this is the trailing vortex. Again, aspect ratio. Now we can see that the larger the aspect ratio, those vortices will be further out. Okay. So if they further out, they will have less effect. What is the effect? Is because these vortices look like that, they creating a downwash on the wing and therefore reducing the 2D lift. So in 3 dimension, the lift will be less. Also, as a result, we're going to have drag, and this is why it is called induced drag. Okay, I don't want to confuse too many of you, but roughly that's where that's the origin of the name induced drag. Here's a bunch of other shapes. Again, we're going to focus only on A. I'm going to give you some diagrams of other shapes, but if you want to do a back of the envelope calculation about what's the lift. Now, we had a problem, a civil engineering problem not too long ago. Scaffolds on the side of the building collapsed because of the wind. And then they tried to calculate what is the force. They say, how could be big force? But turns out that the leading edge of the scaffolding was into the wind. And then when they went through the calculation, well, like we're going to do, you see the forces were huge. So definitely collapsed scaffolding. So civil engineers, you have to know those things as well. Anyway, so summary. So instead, okay, so I want to use the same formulas we used for the 2D case. So we said the lift coefficient is equal to 2 pi alpha minus alpha L0, which this is the camber effect. Okay, it's a negative number. It used to be 2 pi for 2D. In 3D, we basically going to reduce it by the aspect ratio. The smaller the aspect ratio, the smaller this number becomes. Okay, so that's one thing. And this is good for, this is, I said, elliptic, but let's call it for a rectangular plate, that's pretty good. And the drag is going to be friction plus separation. But now we're going to have a significant amount, what we call induced drag, which is due to those vortices pushing the wing down. So the further are they out, which means the aspect ratio is larger, then CDI is going to be less. And if it goes to infinity, which is two-dimensional, it's going to be 0. Okay, so here we have the formula. That's it. That's the whole science I would ask you to remember. Okay, so if you agree to those, okay, let me go back. So this is the science, and let's do examples, okay? So I've been talking a lot, but my intention is try to explain and give you a wider understanding of the situation, which is much more complicated. And then with this set of equation, I'm trying to somehow simplify it so you'll be able to make back of the envelope calculations, perhaps 90% accurate. 95% accurate, okay? Examples, okay. So here's your exam. From the exam, you have a carport, okay, carport. Here's the carport, and it's 3.5 meter long, not long, in this case we call it wide, and then the span is 10 meter. So it's finite. So what is the lift if we have a 20 kilometer wind and the angle is 5 degrees? So now we need to calculate the lift coefficient. It's 2 pi alpha, and it's reduced by the aspect ratio. But the aspect ratio, if you remember, is B over C. So we have B over C. So 1 plus 2, 3.5 and 10, 3.5 and 10. Angle of attack in radians, 5.322. So this is a not large number. Okay, you know what? Let me go back because I did not say something before. One of the reasons I showed you the experimental data is that the range of CL is really going to be anywhere from, say, 0, 1.5, maybe 2, if you have something very fancy. But you cannot have a lift coefficient of 5 or 10, okay? So just bear in mind that this is the range. So if you are in the 0.5, 0.6, then you're somewhere in the middle of that curve, and therefore you're probably more efficient. You're trying to avoid the flow separation, which is happening at the higher angles. Okay, just pay attention to that. So with that said, it appears that now if I have a lift coefficient of 0.322, that's very safe. That's very safe. How much is the lift? Okay, so lift times half rho v square, velocity square, and the area. So lift coefficient, 1/2 rho, velocity square, area. And it's too high, it's like 20 kilograms, 20 kilograms. What is the induced drag? Okay, the aspect ratio is 10 over 2.86. And then we already calculated the lift, and this is the induced drag. So therefore, the drag is going to be 7.5 Newton, which is not very much. In this case, you need to add the drag, which is the skin friction. I would think probably a turbulent one. And what you did in the exam is exactly that case. So the true drag is going to be, CD is going to be equal to this number, 7.5, plus CD0, which you calculated in the midterm, the second midterm. Okay? All right, now let's do just two examples. And there's a little message here about the range of aspect ratio, because I mentioned that if we increase the aspect ratio or the relative width to the chord for the same area, of course, then those vortices are going to be spaced far further away. So the induced effect will be less. So let's have two cases. And in one case, the span is 2. Both will have the same chord. You can have the example made with the same area, but let's have the same chord. So one is 2 and one is 4. Okay, so let me try to do a sketch here. So it is 0.5. Let's say this is 0.5 and 2. So this would be 4 times as wide, which is exactly the aspect ratio. And this is going to be 8 times. Oh, okay, so these are 2 wings that we compare. Okay. So we look at the aspect ratio, B over C, 4 and 8. Okay. The lift slope, 2 pi, and 2 over aspect ratio. 2 over aspect ratio is going to be this. This. So the lift slope is higher, definitely more lift, okay? And then we just calculate the lift coefficient. Well, it's a bit larger, but not dramatically, okay? Same angle of attack. So it comes out, I hope my numbers are correct. It's a little bit more, the lift is more. Lift coefficient. Okay, so now we're trying to do, what is the CDI? So it's pi over aspect ratio and the lift square of the lift coefficient. We do the same thing, or now because of the square, numbers are getting larger, or the difference. And then what is the interesting thing is the lift to drag ratio, which is the efficiency. Okay, how efficiency? So how much drag you have to pay in order to lift something. Here is 42. Here this is 21. Okay, so airplanes, real airplanes, anywhere from 7 to 20 real airplanes. But real airplanes have fuselage, just tails and all that. So this would be just a flat plate, and that's the lift to drag ratio. Okay, if you go very, very large wing, like some of those really high altitude sailplane or drones, or you look at sailplanes, they will have far more efficient wings, and then they could be in the 25 range, including all the skin friction drag of the fuselage and so on, which is pretty good. Okay, let's do another example. So this example serves just to show you that the effective aspect ratio is very important. It's not just increasing the lift, it's reducing the drag, the induced drag effect, and therefore it's really increasing the efficiency. I'm not sure if I should say that, but let me say it anyway, that if you do the algebra mechanics, then if a sailplane or a bird is soaring, then if it's just not doing anything, just trying to soar, then the angle alpha of the slide, okay, is going to be the ratio of drag to lift. Okay, so this is advanced. You kind of remember. If you don't remember, so what it says that if you want to have something that will take a long time to land and kind of fly there on its own, then you definitely need the more efficiency, the higher efficiency. Okay, hydrofoil. So you've seen those hydrofoils. They actually, they're trying to use lift of those little airfoils to elevate the hull of the ship and therefore reduce the skin friction on the body. Let's assume that there are like 2 wings, 4 meter wide and 0.5 meter chord, and the angle of attack is 5 degrees. So here are the 2 wings, and Okay, so assuming symmetric airfoil, 12 meters a second, this is what we would like to. So if you design the ship, then you say, oh, at 12 meters per second, I would like those airfoils to be able to lift the weight of the ship. That's the other way of doing it. But in this case, I'm saying, okay, just calculate what's the weight of the ship. So we go in and aspect ratio, each of those wings is 4 meters wide and 0.5 is the chord, therefore the aspect ratio is 8. So this is pretty good, pretty good efficiency. The lift coefficient is 2 pi, 1, 2 over aspect ratio. This is it, this is the number. I didn't finish calculating. So the lift coefficient is CL is going to be, I just did the numbers and pi square, whatever, this is the number, okay? So we did the CL. How much is the CL of each of these foils? There are 2 of them. So I just copied the CL here, okay? And let's see, so the weight of the boat, according to this story, must be equal to the lift of those 2 airfoils. So let's see. So the area, okay, so I take CL, which I just calculated here. 1/2 rho, which is density of the water, velocity square, and then the reference area. So instead of multiplying by 2, I just added the total reference, which is 2 and 2, which was 1/2 times 4, it's 2. So these are the two airfoil shapes. And this gives us 130, so 13 metric tons, 13.3 metric tons. A lot, that's quite a lot by those little airfoils. The reason is that the density of the water is very large. So now, before I did the air, it was 1.2, but this is 1,000 times more. So with a small airfoil, actually you can lift the whole boat. How much power is required to push the airfoil? And CDI, okay, 1 over pi aspect ratio, 1 over pi aspect ratio right here. And then CL, we ended up with the CL right here, square, and it ends up 0.077. I would think that the CD0 probably can double this number. Okay, double or maybe 2.5 times this number, but just due to the induced drag. What is the force? CDI, we just calculated up here, 1/2 rho V square, or U square, I called it. Here are the numbers, okay, area of the 2 airfoils. 2,000, so it's like 230 kilograms, which is pretty significant force. Power is force, resistance force times velocity. And this is 27 kilowatt, okay, which is about 37 horsepower. Remember, 1 horsepower is a 75 kilogram meter per second. Okay, so it's 75 pi g, because meter is lifting it for 1 meter. So that's kilogram force. So 75 times 4.8, that's going to be something like 740 or whatever. And that's, you divide it, you end up with 37 horsepower, which is not super bad. Not super, it's pretty low. So probably the ship, if I double it, like 40, 80, maybe 100 horsepower motor will do that. Okay, so, which is less than if the hull was completely sunk into the water. Okay. So here we are. Let's get one more. Okay, now this one is a little bit educational, okay, because it's leading us to somewhere which is important. So jumbo jet, I'm not sure if you guys remember the jumbo jet that had 4 engines. That was the first huge engine, a huge airplane, 747, and its weight was 250 tons. These are real numbers, by the way. These are real numbers, 250 tons. And let's say it's landing, it's after the flight, so it's a little bit lighter than before. And like 100 tons of free fuel. And its wingspan is 64 meters, and then the wing area. So I can approximate, it's swept wing, it's a little bit less, which I'm going to show you later, but let's say that this is a rectangular wing, just to have something 90% accuracy. Okay, and the average wing chord is this. So I'm approximating everything by a rectangular wing. And air density is 1.1. Let's say it's landing at a higher altitude. Oh no, this is before it's landing. Okay, so it's at an altitude, that's the density. And his flight speed is 600 km/h, which is reasonable, before landing. It is going to fly probably 800 to 900 km/h when it's up there, high altitude, cruising at Mach 0.8, for example, 0.7978. Okay, so hope you understood what I just said. If not, then it's still fine. So let's see. So we have the lift of the airplane, which is the weight times g, and we divide by 1/2 density, velocity square, and then the reference area, which is right here. And based on our story, the lift coefficient at that condition of 600 km/h, it's almost 0.3, which is reasonable. It's high in a very efficient range still, very efficient range. Airliners are designed to cruise at the most efficient point of the wing, like I showed you on the drag diagram. So we said, let's stick to the rectangular wing formula. And then I calculate the aspect ratio based on these numbers, which I provided. And it's 766, which is true, by the way, for this airplane. And then I want to find out what's the lift slope. It's 2 pi, 1 + 2 over aspect ratio. Plug in the number. It's going to be about 5. Remember, the 2-dimensional slope was 2 pi, which is which is going to be 3.14, so it's going to be 628. So it's 5, so it's significantly less. So 6 to 8. That was 2D. Because of the lower aspect ratio, the lift slope went down. So suppose it's a flat plate. What's the angle of the wind? It's going to be, when I say CL is CL alpha, and then multiplied by alpha, but instead of alpha, I wrote down alpha minus alpha 0. So the effective angle, I just take this number from here, comes out to be 3.4 degrees. So when the airplane tries to approach landing, it's going to be about, let's say, 3.5 degrees, minor degree. And you can feel that when the airplane comes near landing. Okay, so let's keep on going. So that's what our calculations show, that at 600 km/h, the wing is going to need about 3.4 degrees. So now, when it lands actually close to the runway, it really has to slow down. In terms of miles per hour, they are in the 160s, 170, 190 miles per hour, but that's it. So I picked up a speed which is, say, 220 km/h, which is a reasonable speed. Otherwise, you finish the runway before you stop. You don't want to do that. So let's calculate, same airplane, same everything. Only thing we're changing is the speed. So CL is lift over, but now the speed is slower. So plugging in the weight with the G, half rho, velocity square, reference area, 2.2. A moment ago, I just talked to you about, hey, lift coefficients are 1, 1.5, and I'm coming up with 2.2. So you may not like that. Okay. But that's exactly the objective of this exercise. So let's say we leave the wing as is, then I go back to the same formula, which tells me that CL is CL alpha and angle. So this would be a linear slope. And instead of alpha minus 0, I just say alpha, because it's the same thing, right? So if I do this, and of course it has to be radians, I end up with 25 degrees. Anyone landed in an airplane when the pilot pulled it up to 25 degrees? Probably not. Also, I mentioned that on the symmetric airfoil, it stalls at 15 degrees. So going 25, it's kind of very brave, and it's probably going to stall. So it doesn't look good. So the airplane must do something to generate the high lift which is needed without pitching it up. Okay? So that's the whole message of this exercise. And let's see how it is done. It is done by what's called a slot and a flop. Okay? So again, this is a typical data. This is like, I think it comes from Boeing. This is more like a 2D data for the same airfoil or similar, very similar airfoil. And the solid line here is actually the curve that we have when those surfaces are inside or attached into the wing. Okay, so that would be this shape. Now, by extending those surfaces, the forward one is called slot, and then the rear one is called the flap. So we're doing two things. First, we're increasing the area. But in terms of our algebra, we say that the reference area is the same, but in reality, we increase the area. But we also dramatically increase the camber. We also allow some blowing here, which is going to blow on this element and therefore avoid flow separation. So we're trying to, and the same thing is done here because the flow comes from here and otherwise it would separate. So if we have this little blowing here, we're actually going to reattach the flow. So if this thing works like I'm explaining to us, and it should, because airplanes are landing day and night and they're not stalling, then here is the effect. Okay, if you leave the flap in the back and you just have the slot here, then it helps you to increase the angle, and you actually can keep on increasing the angle of attack. And in this particular case, you can almost go to what we calculated. Still, you're going to be at 20 degrees with the airplane, which is not very pleasant. So pilots are not doing that, and actually they cannot do that because there is a program in the airplane that move those two surfaces accordingly. Actually, some of the airplanes will have more than two surfaces, particularly in the back. Okay, now the effect of the back one is significant. So even if I leave the slat in position, just by moving the flap backward and opening it up, we can create a jump of almost 1 in the lift coefficient. Significant increment. If we did not use the slot, we just have it up here, but we already, at that point, which is not, it's not healthy because it's going to be close to stall. We could do probably that very safely, which is going to be maybe CL 1.8. But in our example, we did a 2.2. We did 2.2, so we really want to have on a straight line, which is a straight lift slope, so we must extend the slot as well. In this case, you extend the flap and the slot, and the airplane does not change too much the configuration. Maybe in this diagram, it pitches to 10 degrees, and in reality, it's even less. Maybe the airplane pitches to 7 degrees. That's all, not to the 25 that is required. So the message, excuse me, the message from this example is that you need high lift if the speed of airplane changes. And that is why you have all those strange things moving back and forth. And also lift is really changing with speed. And in reality, we said CL is changing with velocity square. So both lift and drag depend on the velocity square. And if you follow the power for the boat what we did, the power goes with the velocity to the third cube. So velocity is a very important parameter. Okay, so I try to keep on showing you examples and trying to give you more examples on the three-dimensional aspect of these type of problems. So I mentioned that you can look at the lift, and here I put an elliptic shape, because the elliptic shape would be the most efficient, and it's also going to be very close to our calculations, or to the formulas I gave you, and the loading is going to be elliptic. What we have now is rectangular shapes, which we are not, a little bit worse, but pretty close. The point I try to stretch is that we basically created gamma in the little cylinder to create lift, which is, I'm trying to convince you for a week now or more, that it is related to angular momentum. Okay? So if you create angular momentum, you cannot stop it. It actually has to be shed backward. And therefore, we have these trailing vortices, and okay, like that. And I tried to convince you before. So if those vortices exist, then their strength must be pretty much the same as the vorticity that we added to that cylinder. And I also mentioned 2 weeks ago that Mr. Zhukovsky, the Russian gentleman that did this problem with complex variables, showed that you can have a transformation from the cylinder to a flat plate, and it's exactly the same result. So and in that case, the experimental data is exactly lift equal 2 pi alpha, like what we've done. So let's go back to this example. The same airplane. Now it is flying near the ground, 200 kilometers per hour. Here it is. It's a 767. It's a smaller one, but still a large, wide airplane, 100-ton weight. Very significant. Question, or you just, okay, no question. And again, for this airplane, the wingspan is 47, and
the portfolio got 80.
What is the question?
I didn't get anything. Just I get the grade for the.
Somebody's talking there.
But the portfolio, I didn't get anything because
okay.
Somebody on Canvas and they said just send it to me on your email address. So I did.
All right, Miss Janet, what happened to Miss Marianne?
Okay, that was Abdullah Harami is talking and Aldo is talking. Okay, I muted them so we can continue because they're really not listening to us anyway. All right, so here's an airplane flying at a low speed, trying to approach landing. Span is this one. So here's our model, and this is 47 meters. That's what we think. So this is how far. So can we estimate that this number, which we call circulation, this mystic number? Yes, because we said that the lift is rho u gamma. That's what Mr. Zhukovsky said. And therefore, we can just go in reverse and say, oh, let's do that. However, the lift is actually, this is per unit span. This is 2 dimensions, so it has to be multiplied by b, which is the span. That's the total circulation. So I go in reverse, and we have the real airplane, the total weight, okay? And then I end up with the circulation, which is this number. That's some strange unit, but that's what it is. So now I have the strength of that vortex, and this is the same vortex. So now I have a point A. Let's say a small airplane is trying to follow that one, okay? So what is the downwash? The downwash is going to be, remember, the velocity downwash is going to be gamma over 2 pi r. That's the 2-dimensional thing. Remember? That's what it is. So the velocity is going to be distance, which is b1/2. That's the distance of 2 pi r. That's the formula, and then I multiply it by 2 because there are 2 of them. There is the left and right vortex. And it ends up with 4.16, so it's about 15 kilometers per hour. So if a small airplane flies at the same speed, 200 kilometers per hour, he's going to be pushed down at the rate of 15 kilometers per hour, which is not very pleasant. That's why at airports, it usually takes 3 minutes between airplanes to take off. Nobody wants to fly in the wake of the previous plane. And also the airports is oriented such that the wind is slightly blowing sideways, so you're not going to have those vortices. There was a case a few years back when a small business jet flew into the wake of an Airbus 380, which is a huge airplane, and he actually flipped 2.5 times in the air. It was very unpleasant. Anyway, so these things are real, and our calculation is probably 90% accurate or something like that. Okay, so this is just to show that, hey, these vortices do exist. Oh, okay, little airplane. We talked about little airplane. So let's say we have a little airplane and we use the same formula. That's why I have the story rectangular with elliptic spanwise loading. It's a small airplane, 1.2 tons, like a Piper or something. Wing area is 20 meters square, 14 meter wide, and it's flying at 60 meters a second, not very fast. And we can estimate the forward drag as 0.01, okay? So how much is the induced drag? We have to add that to this, and it flies at an altitude. So perhaps the density is a little bit less than 1.2. So how much is the span? Okay, so let me see over there, that one. So we have a little airplane. We say that it's a rectangular wing. The wing area is given. We know how much is B. This one is 14. So this is not rocket science. We have the area divided by 14. We end up with 1.43 for this length here, okay? Which we call the chord. So therefore the lift is going to be the weight. G is important. 1/2 rho velocity square and 60 meters per second. Yeah, it's meters per second. 60 square, and then the reference area. So the CL is 3.71, which again, I mentioned it's a reasonable number. That's typical flight speed of, say, general aviation airplane. So CD is going to be equal to this 0.1, which I mentioned, which is the friction, and then 1/pi aspect ratio, and pi aspect ratio is 9. Why it is 9? Because we take the width divided by the core, it's 9.8. So it's pretty good, very large aspect ratio, and it adds up about 50%. So roughly 1/3 of the drag is induced, and the other 2/3 are viscous drag. So we'd go through the formula, CD 1/2 rho velocity square reference area. There it is. We end up with 47 Newton. So like 50 kilograms, 47 kilograms. It's a force. Multiplied by the velocity, we end up with, okay, this number, watt, divide 735, which is horsepower. So it's about 38.5 horsepower motor. That's what you need. Of course, the airplane will have more power because it needs to take off, needs to accelerate. But then at cruise, it will reduce the power requirement, and it can cruise at a lower horsepower. Okay. So this is what it is. All right, let's study a bird. Same story. So suppose, just my case, okay. So we're watching this bird. It's pretty large, and we think that it flies at 25 kilometers per hour. Actually, we can trace him by one of those velocity measuring devices with laser or whatever. So we kind of know that it flies at 25 kilometers per hour. We know what kind of bird it is. so we know what's the wingspan, okay, which is 0.6. It's like a seagull or something like that. And then again, we go to the biology professor. He's going to tell us that the average chord of the wing is, say, 12 centimeters, something like that. Low altitude, so density is 1.2. And let's say that he's flying at 10 degrees angle of attack. Birds are smart, so they're not going to stall. So if we know these quantities, can we estimate how much is the weight of the bird? Okay, just by looking at it. So yeah, the answer is yes. Okay, so here's a simple model of the wing. Let's say span is 0.6, chord is 0.2, the aspect ratio is 5. So this bird is not super efficient, but some birds are more. Reference area, this is the reference area, 6.12. Okay, and then the CL alpha, 2 pi, 1 on 2 divided by the aspect ratio, we end up with 4.5, very close to what we had before. Lift coefficient, 10 degrees and 10 over 180 pi, because we have to do it in radians, okay? And it's 0.78. So one more time, if you end up with a CL of 52, that's wrong. It should be anywhere from 0 to 1.5. Okay? So we know that the formula, that the lift at steady state is the weight divided by that. So therefore we can calculate the weight of the bird. It's simply the CL, dynamic pressure, half rho velocity square, and then the reference area. And it's going to be 1.63 Newton, 166 grams. Okay, it's like a glass, less than a glass of water. Okay, so that's what it is. Okay. All right, so now if I try to make it more complicated, again, this is more advanced. So I'm just trying to show you more advanced things. But again, if you worried for the exam, we need those simple formulas which I showed you, and so that's it. So what if you have sweep, okay? And actually this diagram was created by the gentleman by the name of R.T. Jones, who almost lived to be 90. And he was a famous gentleman at NASA. Anyway, I knew him. He was a very nice guy. And he created that diagram. And that diagram is very, very informative. Let me see, I have the pen. So here we have aspect ratio, okay, for a rectangular ring. So let's look at a rectangular ring. This is mainly for a rectangular ring. What we did is we said that the lift slope, if aspect ratio is infinity, then it's 2 pi, which is 6/28. Okay, this is the line. Now, if you sweep it, okay, or if you don't sweep it, okay, the formula which I gave you, that CL alpha, is going to be 2 pi and divided by 1 plus 2 over aspect ratio. This is that curve here. That's it. This is this curve. And then from the example we've done, we've seen that we're in the range of 7, 10 aspect ratio. Some airplanes will have 20 or so, but let's say 10. So we could see the drop between the ideal 2D case and then the ideal 3D with the finite wing. That's what it shows. Now, next, it shows also if we start sweeping the wing backward. So if you sweep it back 45 degrees, you lose that much. If you sweep it back more, you lose even more. So you have this, or I have this. So the swept wing will have less lift than the straight one. That's the result of that conclusion. Again, if you do the numerics, it comes out exactly the same way. Now, there is one more thing here in this diagram is that I didn't mention it very clearly, but what we did about these cases with the aspect ratio, they usually threw anywhere from 3 and up. When the aspect ratio is very small, something like this, then it's really starting to be something else. So it's not really very good for that. So Mr. R.T. Jones developed a formula for something which is much smaller. So the flow comes here, so which is less than 1. And he came up with this formula, which is a slope. So he kind of completed that diagram. And he said that you take the aspect ratio, pi half aspect ratio, so that would be the CL. CDI will remain the same. Again, we're not going to use that formula. This is called slender wings. And this was originally developed for delta wings. Okay, this diagram was created when the high-speed era started. Back in the 50s, people started thinking about flying supersonic. And then you need to land and you need to have the smallest swing possible. You have to sweep the wing back. Again, it's shockwave story. So this is where he became very famous. Anyway, this is history. Those that were interested, this formula is kind of, okay, approximation. I will give you a more accurate formula in a minute. So the point is that sweeping, you lose, straight is the best. And of course, other shapes, you have to do the calculation on your own, which you'll be able to do once you do a PhD in this area. Now, speaking of slender wings, something else is happening. Because the wing is very slender, the flow goes from below above. Oops, I touched it. Goes from here. So high pressure below goes here, and then the same story I told you before, it creates those vortices, but now they are on top of the surface, top of the wing. And actually they increase the lift of the wing. And either it's a delta or a rectangular, you still have the same phenomenon. So there is an experimental formula. Again, this is not going to be in our exam, but if you really want to do that, this is for angles of attack larger than 7 degrees, maybe 10 degrees, 20 degrees is going to work. And then here's the formula, A1 and A2, and they change only for this case, so case A and case B, and here are the numbers. And then what we have is simply CL tangent alpha, which means that the force is due to pressure, and forget about the story about the induced drag. So it's simply the tangent. Now, there is another anecdote to this, is that once you develop those vortices, they create suction and then they lift the surface. So suppose you have a missile and it has this ring here, it has a certain lift. And then which is going to be this curve. This is the lift. So we can see that because it's a very flat plate, so it usually starts stalling about 8 degrees, 9 degrees. But if you add those little streaks, little sharp things here, they create these vortices here. And then the vortices keep on going on top of the wing. The suction of those vortices will increase the force on the wing. And in a sense, you're going to have much more lift, not because of the lift on those surfaces, but because of the additional lift on the wing, which is a very interesting phenomenon. So you get augmentation. Again, this is a storytelling part, and you're not going to be questioned in the exam. But those that want to learn something, I'm just providing you that information. I think next we're going to have some examples about using the trick of slender bodies and vortex lift. And I delay it for Tuesday. We'll do it on Tuesday. I think we should probably wrap it up with materials. Any questions if some of you are still there? or not napping.
Well, Professor, I have a question, but it's not about the material today. It's about the exam because of my special case.
Yeah, go ahead.
Oh, okay. Because I had to turn it into you because I had to take the test a day after. Do you know when I'm going to be able to get the grade for me?
Oh, and exam 2.
Yes, exam 2.
Exam 2, we promised that we're going to give the grades back by first week, by the beginning of next week.
Okay.
So you included, everybody.
All right. Because I don't know if it got sent to the homework guy or the test guy because I sent it to you.
We'll have it. Don't
All right.
worry, we'll have it. It's
Thank
a
you very
matter of
much, Professor.
sending it back. Okay,
Thank you.
you're welcome. Any more
Professor, I had
questions?
a question about the final. For the final, do you know, because I know we have 2 hours for the exam, do you know, if it's going to be, similar length to the regular exams, or if it's going to be longer than, the regular exams? How many questions should we expect for the final?
I probably will do 4. I'll probably do 4. I'm still not sure if we're going to have the full 2 hours, or let's try to stick to an hour and a half. I don't know what you guys want, what you guys prefer.
2 hours would
2
probably give us more
hours.
time.
2
So we
hours
can-
sounds great.
So we can check our work.
check our work and we can take our time on it.
We can talk about it next Tuesday because I've seen some of the students leaving. So if you raise that question Tuesday, we can decide if everybody wants to. Again, university rule is 2 hours. It's a bigger, so I have to make more complicated questions. But if you want to stick to questions like exam 1, exam 2, then we can make it shorter. It still will count more, like we started at the beginning. But anyway, so.
But you're saying if it's 2 hours, we'll have a harder exam or longer?
Officially, university, I'm looking at it again. I hope I looked it up properly. I found out that Tuesday, 15, 3:30 through 5:30, that's where the final is for this particular course.
No, I understand. I'm just saying if we chose the 2